Okay, so next generation wireless, if I have to ask what are the few things where it will differ, I will put these 4 bullets. In terms of operational space, what are the differences? In terms of spectrum usage, what are the differences? In application space, what are the differences? And physical layer waveforms and physical layer techniques wise, what are the new things? First thing is operational space. Compared to 5G, 6G is going to be growing vertical. When I say vertical, 3 communication. In other words, users are not going to be in terrestrial world itself. They may be in 3D also. For example, the platforms may be drones. The platforms may be UAVs. And it could be through, platforms can be in airplanes, LEO satellites, and so on. So there's going to be a confluence of terrestrial and non-terrestrial networks, which we call these NTNs. So which is going to be the order of the day when we go from 5G to 6G. So particularly drones and UAVs are very popular for various other reasons, both commercial as well as tactical, right? From military point of view, drones are important for, various reasons. For commercial point of view, we have delivery and other applications for drones. So one characterizing aspect from a communication engineer point of view is all these platforms are going to be characterized by high relative velocities in terms of their speeds. So we will come to that, why they are important in the next few slides. Okay, so that is about the operational space. We are not going to, drive and then talk. You are going to have many things like fly and talk in, airplanes, and then your base stations can be in drones, and your relay stations can be in, for example, your RIS themselves can be on drones or UAVs and so on. In terms of spectrum usage, I think we are very comfortable so far up to 6 gigahertz and below kind of frequencies. And in 5G, there was an attempt to go to 28 gigahertz, and it was not very successful. Although 28 gigahertz technology was there as device technology, but propagation, beamforming kind of issues did not make it as a big success. So it remains so. 6G, whether 28 gigahertz will be taken far, we do not know. But sub 6 gigahertz will continue to play a big role, number one. Now, same thing is true for when 28 itself we had difficulty, 30 gigahertz, 60 gigahertz is going to be even more difficult. So it is going to be opening its, mark in the future days. So we are not sure. And another thing from a research point of view is terahertz is opening up. And from a research point of view, it is good. And we expect a lot of academic institutions and companies spending research on terahertz devices and so on, right? But as such, 6G may not be on terahertz, but a research opportunity nonetheless. In the application space, I think so far EMBB in the 5G triangle, EMBB, MMTC, and URLLC, EMBB has been a prime driver so far. And we may expect something similar to happen. And why would that happen? Because of these new technologies of this AR, VR, and XR technology. And holographic communication is a widely anticipated XR use case. And we go to any technology show these days, they have these, AR, VR kind of demos from a lot of startups and big companies. And the integration of those technologies for along with mobile networks may happen. Digital twin, metaverse, these are all upcoming applications. We do not know which one is going to be a sustainable and profit-making application for 6G and beyond. But you always search for new use cases. You never know when a big use case will come and hit you. But application space is going to be also very important. And the physical layer space is where many of us do research, including RIS as the last bullet in that physical layer space, reconfigurable intelligent surfaces. Waveforms, integrated sensing and communications, they are all coming under new physical layer techniques and methods that can come in 6G. Now, I may ask one quick question. Reconfigurable intelligent surfaces have been talked about for beamforming, probably in the last speaker's thing. Did anyone talk about modulation being one of the applications of RIS in the last couple of days by the speakers? Okay, so let me take that question when, yeah. Okay, let me come talk when it comes to that. Now I'm moving my slide. I'm in slide number 6. Okay, so slide number 5, can you see?
Yes, sir. Slide number 5 we can see. Now we will go. Yes, sir.
And now slide number 6.
Yes, sir. Yes, sir. It's visible.
Very good. So what I would say is straight away start from where we are now. Where we are is OFDM. Okay, many of you may be teaching OFDM in your classes or doing projects for various agencies and companies for in OFDM, and you may be giving projects to students in OFDM. So what is OFDM is all about, and where it scores and where it doesn't score, right? So for example, okay, sorry, this is blocking my way. Yeah, maybe this is better. Okay, so what I have here is the doubly selective channel. I think when I say doubly selective channel, fading channels can be characterized as frequency selective or time selective. Okay, and we know the definition of that. I assume that the definitions are known. Okay, and OFDM is good for frequency selective channels. A frequency selective channel, as in the first two figures, the left side figure shows the tab delay line model of a frequency selective channel. When S of t is what is the transmitted signal, this whole block diagram is looking like a FIR filter, and that is essentially a representation of a frequency selective channel, and it has multiple paths, in this case L paths, and they are delayed by certain delay T in each tab, and then it's going to have some gain, which is going to be having some distribution, that is H0 of t, H1 of t, and so on. And they all delay, multiply, and combine will give you Y of t, which is the output, and that is going to be a frequency selective channel output. In the frequency domain, how that will look like is on the right hand side of this picture, which is going to be time, frequency, and magnitude. Okay, so when I say frequency selective, if the channel response is such that it varies in the frequency domain like what it is showing here. Okay, so there is variation in the frequency domain along the frequency axis in this figure, so I call that as frequency selective. In addition, if the channel also changes along the time axis as what is shown, it is both time selective as well as frequency selective. I call that as doubly selective. Okay, so keep this because we will be going to repeatedly talk about doubly selective channel as we move forward. Okay, so we know that OFDM, as I've shown this block diagram here, is essentially modulating the symbols in the frequency domain, right? When you say X of F here in the left hand side, right, that is the block of symbols, which could be the modulation symbols, QAM symbols, 4 QAM or 16 QAM or 8 PSK or whatever. You collect certain number of information symbols, pretend that they are in the frequency domain for whatever reason to work well in the frequency selective channel, right? Pass this n information symbols through an IDFT operation. An IDFT operation converts frequency domain to time domain and add some cyclic prefix to get parallel channels out of this whole exercise. And then, yeah. Any
Participants
questions?
will take the questions at the last, at the end of the section. Please mute yourself. Sir, we'll take the questions at the end of the section. Please continue, sir.
Okay, so that time waveform is transmitted through the frequency selective channel. At the receiver, you do the remove the cyclic prefix and do a endpoint DFT operation, which changes time domain to frequency domain. And this Y of F is the frequency domain representation of the signal where you do modulate the symbols. Okay, this is good, right, for frequency selective channel because OFDM can handle the inter-symbol interference that is going to be caused by frequency selectivity. But if the channel is time selective also, then the resulting effect is going to cause inter-carrier interference. If there are n subcarriers, 1024 subcarriers or 256 subcarriers, between any two subcarriers in this block, there should not be any interference. In other words, project one subcarrier onto any other subcarrier, the resultant dot product should be 0, right? If that is not 0, there is going to be non-orthogonality. That orthogonal wave frequency division multiplexing happens because of that O. First O is because of the IDFT and DFT operation, keeping the subcarriers to be orthogonal to each other, right? But when there is time selectivity, that orthogonality will be lost. And that is because inter-carrier interference is going to be created, and that is going to make OFDM to perform poor in highly time-selective channels. Recognize this is a bullet point. In highly time-selective channels, OFDM is not going to do well. In frequency-selective channel, it is going to do well because it is designed to do well. Okay. A second problem with the doubly selective channel, particularly the time-selective nature, is I have to estimate the channel. That estimation is going to be difficult if the channel is rapidly varying, because at this instant in time, I want to sense what is the channel. I send some resources as pilots, and then it comes and then I do some processing and then estimate the channel. There is some delay involved in this, and delay, if it is going to be comparable to that of the time variation of the channel itself, then that channel estimated is going to be no longer accurate in the instant when I'm going to use. So in other words, your channel estimation in time varying channel is also a problem. Okay, this is to say 4G, 5G are good, but they may not be adequate as we go beyond. This is from a new waveform point of view. Why is from this simple diagram, we have the increasing Doppler frequencies across different generations. This Doppler frequency we know is going to be the relative the frequency shift between the transmitter and the receiver due to velocity, right? The Doppler between transmitter and receiver is this carrier frequency times velocity divided by speed of light. So both carrier frequency and velocity are in the numerator. So if velocity increases, Doppler increases. When carrier frequency increases, Doppler increases. Now FC is the carrier frequency. Let's say if it is 4 gigahertz, then what you see here is our 5.9 gigahertz, for example, even in 5G today, if the blue curve, which is about 150 kilometers per hour in the freeways if you drive, then the Doppler is in the order of 800 hertz or less. In other words,
sorry
up
to
to
disturb you,
4G
sir.
and 5G.
Sir? You
Yeah,
are in slide number
yeah.
6 only, sir.
I'm in 7. Sorry, I think I didn't check.
Sir, can
you see?
yeah,
Can
we are in 6
we
only.
see?
Can we reshare it once again, sir? Can we
Yeah, I think that is a better idea, because I think it
yes,
is
sir.
going to be a difficult exercise. Okay, stop sharing. No. Okay, it is now I've unshared. Now I'll share again. Maybe I'll
Actually,
share.
right now I can see your screen numbers. Slide number 7.
I don't know. There's a big lag, so I don't know the WebEx. Is it for
Also,
me
you can
only,
try
or
PDF also. You can try PDF also. Sometimes PDF
Yeah,
works
now
better.
the participants, can you please mute your mic? Now it's done, sir. Now you need to try to reshare it again.
okay? Let's see. Okay, so let me share window. Okay, so now can you see my slide?
It's loading, sir. Just will give 2-3 seconds to. No, sir. We didn't get it. We'll wait for 5 more seconds.
I think we should fix this before we move, because otherwise we'll be spending a lot of time on this.
Yes, sir.
You are able to see or no?
Still no, sir.
Okay, I don't know what. Last time I did the
So you
same
can
thing.
try PDF also if PDF is available on the slides.
Now I'm opening PDF only. Can you see? Can you see what I'm sharing now?
No, sir.
No.
Actually, sharing
PDF.
has been not done. For us,
It's
it's
a,
showing like main screen of my own screen. So I
okay.
think
I say it's sharing and stop. I'm stopping. Optimize text and images. Click share to share. Share. Chrome tab. No. Okay, this is not entire screen. There are three options which will work. There is window and the entire screen. Which will work better? I tried both.
window. Sir,
So
window
window,
you try, sir. Window means it
yeah,
completely whatever you share, it will show
yeah,
us.
that's what I did. I've been using now after in meeting, and let's see, share.
Otherwise, you can try the entire screen.
Now it says connecting. Let me do one thing. My internet is good. Let me move from EduROM to, okay. You want me to disconnect and connect because internet, is that the reason, or I'm connected to EduROM, but there is
Okay,
a
sir. Okay,
IISc
sir.
network also
Okay,
which
sir.
I
You
can try.
reconnect once again and we'll try it, sir. You just disconnect
Okay,
and
so I will do
connect
that.
again.
I'll do that. Okay, so sorry for that.
No, it's fine. Okay.
So leave the meeting. Okay, I've joined now. Can you hear me?
Yes, sir. I can hear you, sir.
Let me share once again. Let's see whether this time the network I've changed. Trichy. About the slide. Can you see my
Yes, sir.
slide?
Yes, sir.
Yes,
Now I
please.
can see you,
Slide
sir.
number
Slide number 7.
slide number 7. Okay.
Yeah. Yes, sir.
Okay, what I did was I changed my network. Hopefully that was the reason and that we fixed it. We could have done, I could have the network in the beginning itself. Okay, so what I was saying was Doppler shifts are going to be a reason for time selective channels, particularly if Doppler is going to be determined by the carrier frequency operation and velocity of the relative velocity between the transmitter and the receiver. We are going to have high velocities. The summary of this slide is to say up to 4G and 5G, the Doppler was between few tens to few hundreds of hertz, 200 hertz, 100 hertz, 50 hertz, and by mobile pedestrian 5 hertz, 10 hertz, and so on. But 6G and beyond, if you see here, if you go to high speed, even at 4 gigahertz, right? Even at 4 gigahertz, if I have bullet train speed, which is 500 kilometer per hour, which is this magenta color, you have 1.85 kilohertz of Doppler. So in other words, we end up having few kilohertz to tens of kilohertz of Doppler. For example, if you talk about Starlink, the LEO satellite speeds are much faster. And if you want to have mobile connectivity using that, you are going to have very high relative velocities of the order of tens of 30 to 40 kilohertz of Doppler. So we are going to see very highly rapidly changing channels, right? And what it tells as academics is we are so far working under the regime of linear time invariant systems, which we teach to our students in signals and systems, LTI systems, where convolutions work. Fourier theory is the transform to Fourier theory is the theory to explain that. And although we say LTI system, you may ask a question, we are using in a mobile world. Are we not having a time varying channel? And why are you saying that the 5G, up to 5G, the signaling that we are doing is under the framework of LTI, right? We already have 100 hertz, 200 hertz, 500 hertz of Doppler. Is it not time varying? Okay, the answer to that is we assume that the time variations are slow, right? Which means we have within one block of data that you are going to transmit, the channel will not change much. That is the assumption we are making. We say the n subcarrier OFDM system. So we say that it's going to be 1024 subcarriers, right? And you are going to send these 1024 subcarrier symbols in 1024 channel uses as a block. That block time duration is going to be something which is going to be determining the LTA or non-LTA nature. So if the channel is not changing within the frame time or the block time, we assume that still over the block duration we can do, and we can assume that it is LTI channel and apply all the superposition, convolution, Fourier transform theory behind it to design system, and that's what you have been doing. But in 6G, when you talk about these high Doppler spreads, it is no longer true that it is not going to change within a block time. So now the rapid variations are going to change, and the framework is not going to be LTI framework, it is going to be LTV framework, linear time varying framework, which 10 years from now, if you have to teach, you may have to teach in signals and systems using linear time varying system models. Now we are teaching linear time invariant systems using superposition, homogeneity, and convolutions and Fourier transforms. Now we may have to do something different. And what is that? That is more towards a new modulation technique, which we are talking about more in the recent days. What is called as OTFS modulation, and that is appropriate for linear time varying channels. And the transform corresponding to that is going to be a Zach transform in place of a Fourier transform. And the convolution operation that we normally apply to analyze linear time invariant systems is going to be something called twisted convolution in the delay Doppler domain, right? So these are changes which are very fundamental, and they are going to be applicable to new generations beyond 6G or even 6G. Okay, so I moved to 7, 8. Can you see 8?
Yes, sir.
Slide number 8.
Yes,
okay,
sir.
very good. So what I have shown here is the new waveform, which is going to be talked about in terms of delay Doppler modulation, which we say that suppose if I have a time selective channel and a frequency selective channel, you have a response which is on the left side, which is saying it is changing in frequency domain as well as time domain. So that is TF domain. A channel has a response which is the H of TF, right? We say H of T is the time domain impulse response of a system. Now we have T comma F, and that is this yellow diagram that is here. It is changing in both the time planes, time as well as frequency. But that is difficult to track in channel estimation, and difficult if the time variations are going to be very rapid. Now the same channel, take a symplectic finite Fourier transform and view it in the delay Doppler domain. This time frequency domain has a Fourier symplectic finite Fourier transform relation to delay Doppler domain. And if you view the same channel in the delay Doppler domain, two things are very simple, easy, important. One is going to be, it is sparse, channel is looking sparse, and channel is also going to change slowly with respect to time. So these are inherent in the way we are looking at the channel itself. So this I think is important, and this will help us to do new waveform design in the delay Doppler domain. And that is one of the highlights of, I would say, emerging technologies to take opportunities in research, writing patents, writing, developing prototypes and so on. So this diagram at the bottom, I will come to that later, but recognize that delay Doppler domain is where I want to do my signaling as well as my representation of the channel. I have now moved on to slide number 9. Can you see?
Yes, sir.
Yes, sir. Okay,
Okay,
yes.
now I think now it is clear. Okay, so the way I look at this delay Doppler modulation is through this new modulation called orthogonal time frequency space modulation, and it is a promising modulation for doubly selective channels. And in here you mount information symbols in the delay Doppler domain as compared to what we did in the OFDM. In the OFDM we multiplexed the symbols in the time frequency grid. This blue grid, right, is what I have in OFDM. It is time axis n slices, frequency axis m slices, and delta is the subcarrier spacing along the frequency axis. And there are mn grid points here. In each of these mn grid points, you mount one QAM symbol or modulation symbol, that is OFDM. After mounting this, you pass it through IDFT and then convert it in time and transmit. Instead, in OTFS, what you do is mount on this red grid, and that red grid is a delay Doppler grid. X-axis is a Doppler axis, y-axis is the delay axis, and you can say n delay bins, m Doppler bins, and the delay bin width is 1 over m times delta f, where delta f is the subcarrier spacing again, and the resolution or the spacing between two Doppler bins 1 over nt. And we multiplex information symbols on this grid, right? And that is one fundamental change, right? In 2G and 3G points, symbols were mounted in time domain, okay? In 4G and 5G in OFDM, symbols were mounted in time frequency domain. And going forward, if you adopt this kind of modulation in OTFS, we will be multiplexing the symbols in the delay Doppler domain in the red grid that I have shown, where there are mn delay Doppler bins, and I will mount mn symbols using m into delta f resources of bandwidth and nt time duration. If you see here, for the blue grid also, nt is the time duration and m into delta f is the resource for bandwidth. And for delay Doppler modulation also, same resources in terms of time and bandwidth. Only thing is the domain in which the symbols are multiplexed are different. Now I cannot transmit delay Doppler signal as such into the channel. All physical channels, time channels, you can send only time signals. Okay, there are two schemes which convert these delay Doppler symbols to time. Okay, just like in the previous figures we saw, OFDM was converting capital X of f to X of t using IDFT. Here I have on the left hand side XKL. It is double indexed k comma l. One is delay, one is Doppler, right? And I convert that into X of t here using here two transforms. One is inverse SFFT to convert delay Doppler to time frequency, and then time frequency to time using Heisenberg transform. This is one approach which we call this as a multi-carrier approach, which is backward compatible to current OFDM system, because this Heisenberg transform and Wigner transform at the receiver, they are the current time frequency modulation like OFDM. Okay, so at the outer place you put a conversion from delay Doppler to time frequency, and the receiver you convert from time frequency to delay Doppler using ISFFT and ASFFT. So this from 2017 onwards till today, it has been researched and it has shown that MC OTFS is good. Multi-carrier OTFS is better than OFDM. So that's one approach. Another approach is to say, I take this XKL, but don't go through this two-step process. Go in a single transform, which is a ZAC transform. You take a delay Doppler symbols, apply inverse ZAC transform to that, and then convert that into time domain, which is X of t, and transmit it through the doubly selective channel here. Everything is doubly selective because with frequency selective channel alone, you are okay with OFDM, right? But when it is doubly selective, it is not probably okay, is what the message is. So receive time signal, you convert that back to delay Doppler in ZAC using ZAC transform, and then do the demodulation in YK, right? So
Participants, please mute your mic.
thank you.
Yes, sir.
Now, yeah. So now these are two things. Now the more recent research is on ZAC transform approach, which we call this as OTFS 2.0 or ZAC transform based approach, which is ZAC OTFS. So now I will spend a little time on ZAC OTFS, right? Because that is more recent and it is better than MC OTFS. So look at this diagram. I think I'll give the highlights. I have delay Doppler bin, right? This left side corner diagram is delay Doppler. X-axis is delay, y-axis is x-axis is Doppler, y-axis is delay. And there are n slices on x-axis and y-axis you have m slices. And in each grid point, I am going to use a waveform which is a delay Doppler pulse, right? When I say a time pulse, right, I say it is along the time a rectangular pulse, right? If I say a frequency pulse, a rectangular pulse or an impulse in the frequency domain. Now I'm talking about a pulse in the delay Doppler domain. So it is going to be having on the delay axis a pulse which is having a rise and fall. On the Doppler axis also there is going to be a rise and fall. Together it will look more like a nipple, right, of certain narrow width, and narrower the width, as you keep increasing the width to 0, it is going to be an impulse in the delay Doppler domain. And the basic carrier in OTFS or delay Doppler modulation is a delay Doppler domain pulse. Okay, we know time domain pulse, we know frequency domain pulse, and now I am talking about a DD domain pulse. Okay, DD domain pulse, on each of those pulses I will mount one symbols. So there are MN delay Doppler pulses separated by delay and Doppler shifts, as you can see in this picture. Like in OFDM, you had the grid points, delay and time and frequency shifts, you had points in the time frequency grid. Now you have delay and Doppler points which are separated, and on each of those points you have the symbol, MN symbols. Now this I do convert that into time domain using inverse ACT transform shown by this modulator block here, right? So there is going to be a DD information symbols and inverse ACT transform, and there is going to be a time domain signal. And that time domain signal, okay, how does that signaling signal in the time domain look like? For example, if I have a frequency rectangular pulse, if I take in the frequency axis a rectangular pulse, how does it look in the time domain? And you immediately you will, from your signals and systems, you'll say it is going to be a sync function in time domain. That is a waveform in time. A rectangular frequency pulse in time domain is a sync waveform in the time domain. Likewise, if I ask the same question, you say that you have a delay Doppler pulse and it is looking like a cone, right? And I want to see that in time domain. How does it look? All you have to do is take a inverse ACT transform and see the output, and that will look like this diagram on the right hand side, which is a train of impulses or pulses, time domain pulses. This is time axis. In this diagram, this is time axis, and there are green spikes which are the pulses in time domain, but they are not constant amplitude pulse train. It is going to be a pulse train whose amplitude is going to be modulated by a sinusoid, complex sinusoid. Now I have shown one real part of it, which is a sinusoid here, right? This we call this as a pulsone. So in other words, if there are MN symbols in this grid, I will use MN delay Doppler pulses or MN pulsones in time domain to mount each symbol on that. In other words, MN pulsones are there. On each pulsone, one COM symbol will be there, and different pulsones are going to be different, which are going to be shifted in time and delay, in delay and Doppler. Okay, so I hope that I conveyed that message. And why do we then have to worry about OTFS? OFDM is working fine. A lot of people are still feeling OFDM is good. This picture is an old picture that we published a while ago, and that shows in a channel which is having the current LTE or 5G kind of waveform. If my wave Doppler is 1.87 kilohertz, 1.875 kilohertz, 500 kilometer per second bullet train speed, right? My performance for OTFS is this blue, and my OFDM is this red, which is to say that OTFS is more robust than OFDM to time variations. In other words, the statement that we said that it is going to be good for doubly selective channel is emphasized by this performance graph. That is number one. Next, I'm in slide number 13. Can you see? Can you see
Yes,
slide number
yes,
13? Okay. Sorry, I'm double checking. Okay.
Yeah.
Why ZAC OTFS compared to MC OTFS is to say that here, first of all, MC OTFS has some transforms to it, but a more formal theory is in ZAC OTFS. Let me put it this way. MCOT, first of all, we are growing out of OFDM conceptually, academically, research-wise. Okay, industry and standardization is a different ball game altogether, right? We have to address different issues there in terms of quality, complexity, cost, timeliness, and all those things. But we are academics, so academics can be a little more flexible in their choice of statements. So OFDM is no good for doubly selective channel. OTFS is good. MC framework, MC OTFS framework itself is good, but ZAC OTFS is even better for two reasons. Like Fourier transform theory is to OFDM, ZAC transform is to OTFS. LTA is for OFDM, LTV is for OTFS, right? This makes the difference. So LTV versus LTI, ZAC transform versus Fourier transform, and high mobility scenarios are going to be handled better by the naturalness, which you read papers and then start doing research, you will come across. The difference between MC OTFS and this is ZAC OTFS is ZAC OTFS is more robust for a wider range of Doppler. Here, if you see, the uncoded bit error performance is much stable over even up to 4 kilohertz of Doppler, it is stable, whereas for MC OTFS, it is better than OFDM and FDM and TDM, but it is still not as good compared to ZAC OTFS. So there are a couple of papers that we wrote recently into 2022 and 2023. I would request you to go through if you're interested. And even more interesting thing could be something which we published very recently, last few weeks, December 2024. We published book on OTFS modulation theory and applications. Myself and Ronnie Hadani is one of the inventors of this modulation. He's a applied math professor in Texas, Austin, and also the co-founder of a company which spearheads this technology. And Saif Khan Mohammed is a Delhi IIT professor. So feel free to take a look at these topics. And this makes me to end my first part. Are there any quick questions? Because what I'm going to talk about is going to be a different topic.
Okay,
I can take one or two quick questions.
Yes, sir. There are two questions in the chat box. I will just go through it.
Mm-hmm.
Sir,
Right.
whether can we expect non-orthogonal multiple access rather than orthogonal multiple access in order to achieve better spectral efficiency?
The answer is yes. NOMA will give better spectral efficiency compared to orthogonal multiple access. And the only drawback which can be overcome is the increased complexity in terms of receivers have to do with interference cancellation, and detection complexity may be high. But the answer is yes. NOMA will be better in terms of spectral efficiency compared to orthogonal modulation schemes.
Yes, sir. I will continue, and if there are no more questions in the chat box, we'll get back to you at the
Okay.
end, sir.
Very good. Okay, so now RIS is the second topic I want to talk about, but then I will restrict this a little bit in terms of basics. I think I will focus on, now this picture you are familiar, there is a base station, there is a receiver, and there is not a good link between them, and RIS can help through a reflection from there, and that RIS is going to have multiple elements, and those elements are passive elements, low cost elements, many of them, and they can be tuned in their phases by electronic means. Typically, these devices are diode. For example, they can be switched on or off, right? Using a diode being in on state or off state, right? Or you use a certain phase to be applied to these devices, and they can change the reflection characteristics of the impinging EM wave. And it increases the signal to noise ratio. It gives signal quality enhancement. Coverage is better. Energy efficiency is better. So you know all about it in the last 2 days. Okay. So what must have been emphasized is the RIS elements are passive. So which means there is no RF up converter and down converter. In any communication device, if it is a wireless device, your radiation is through EM compatibility is through an RF element, which is converting the baseband signal to RF signal. Okay, and RF signal to baseband signal. Particularly transmitter means I have baseband signal, I have to up convert it to whatever the frequency I need to, and then transmit it. So it needs up chain, including power amplifier, which is expensive. We call that as active. But passive, there is an amplification, we call that active. Passive means it simply reflects. It doesn't have this up conversion. EM wave falls on it. EM wave is reflected by some element because of its characteristics. That's all about it. Low cost, right? But it can be channelized towards receiver in a certain way if you calibrate it carefully using the phases that you want to choose for tuning, right? Now, passive is one. A lot of papers have been written. I think it's a very highly volatile, or not volatile, I would say very dense area where a lot of papers have been written on RIS. The fact that you run one full FDP on RIS itself is an indication that so much of material is there to know and do research on and apply. Now, the next thing that I want to say is you need not restrict yourself to passive elements in the RIS. I don't know whether anybody talked about active RIS, and I'm going to talk about two things which are probably not touched upon. Even if it is touched upon, I want to emphasize in the way I want to emphasize. Okay, one is the active nature. In other words, each element can do either phase tuning only in a passive mode, or it can do active mode, which means it can do phase tuning also. In addition, it can do an amplification. Okay, so that we call that as active RIS. So now slowly research papers are moving towards active RIS, which is to say that elements can do phase tuning as well as amplification. When there is amplification, there is more hardware, there is more power, there is more cost. So it takes away some of the advantages of this passive RIS in terms of economy, right, in terms of cost and so on and so forth. But it brings and addresses one important question. This I will skip because this I think many people would have told you, right? It gives an array gain, which is a beamforming gain. Can you see 17, slide number 17?
Yes, sir.
Okay, so the first bullet is what I want to emphasize. Can you see the first slide, which says array-sided systems can suffer from multiplicative fading? What do you mean by multiplicative fading? Is I have transmitter to receiver. There is one path from transmitter to RIS, and the channel gain, let's say I say H subscript R. The path loss or the fade coefficient from transmitter to rth element in the RIS, call that as HR. And that same rth element to the receiver, it has a different path coefficient, which is GR. So effectively, you have a path fade coefficient, which is the product of H and G. Okay, and if H and G, if any one of them is in a deep fade, you end up having still a problem, right? So there are reasons to believe, depending upon the position. I think there are people like Abhishek Gupta who talked about placement of the RIS is crucial, right? Because I've listened to him in a couple of other talks. He focuses on how to place RIS in such a way that these effects are going to be not taking away the benefit, so-called RIS. So multiplicative fading is one, in the sense that if G is in deep fade or H is in deep fade, the overall fade is going to be even deeper. So that is what we call this as multiplicative fading. And that multiplicative fading can be countered with some elements to be made active, in other words, amplify, right? That is active RIS. So we say use of active elements helps in mitigating multiplicative fading. An active element amplifies signals in addition to phase tuning. Okay, so this is one message, whether it has been conveyed or not, but I am conveying. If it is a repeat, take it. Now I'm going to use this active for two reasons, right? I'm going to use it. Okay, multiplicative fading can be alleviated using these active elements. Now these active elements also can be used for modulation, because so far RIS has been viewed as a distributed beamformer. In other words, you say that there is a beam which can go directly with a high gain towards the receiver, and that is not going to be engineered at the transmitter. It is going to be engineered at the RIS, which is at a distributed different place, either a wall or a ceiling or some other object which is specifically placed as an RIS. So it is a distributed beamformer, right? So now, in addition to that beamforming advantage, these active elements now can create opportunities to do modulation. A new method, which I think I have put this into the 2023 paper by Basser and his group, is hybrid reflection modulation. I'll highlight that in a small form and then let it go. Hybrid reflection modulation is something which I want to highlight. Another one is media-based modulation, which is an older technology than RIS, but it does convey modulation. But I'll, depending upon my time, I will skip it or use it. But I'll talk about the hybrid reflection modulation because it is in tune with the program's topic. Okay, I have 30 more minutes, 6 o'clock now. Let me spend some time on this. RIS for modulation. There are 3 slides. Just follow me. I have to convey information bits to the from the transmitter to the receiver. What is my objective? There is a transmitter, there is a receiver. I have to send bits from transmitter to receiver. Suppose RIS is not there, there's a direct link. What I do, I take information bits, modulated using QAM or PSK symbols, upconvert it using upconversion, and then radiate it and receive it demodulated. So that is a conventional. But now this direct path is not available, let's say, and RIS is going to help. Because of that, now I have bits modulated using QAM, radiated using the transmit antenna. RIS tunes itself to direct that symbols towards receiver with high gain, and that is RIS, which is passive. But this block, which is the information bits, which we call the hybrid reflection bits, HRM bits, hybrid reflection modulation bits, which is extra. Okay, and that, how is it going to help you? Together you view this RIS, you believe or you pretend that it is to be a single transmitter, although RIS is far, and assume that information bits are going to be tagged together, meaning there is going to be a wire which goes from the same source to feed the information bits to the RIS. Pretend that that is going to be there, right? Now how I use this RIS is, look at this diagram on the top. I have how many elements? Each blue square is an element. 32 elements in this. N is 32 elements. Okay. What I do is I convert that into slices of tiles. I would say make these 32 elements into 4 tiles. Tile 1 has 8 elements. Tile 2 has 8 elements. Tile 3 has 8 elements. Tile 4 has 8 elements. Okay. This is an example. In other words, I have 4 elements as tiles. No, 32 elements partitioned into 4 tiles, each having 8 elements. Now, I'm going to use this for conveying information. So what I'm going to say is, in a given time, how many tiles are going to be active, how many tiles are going to be passive, I can choose. Okay, right now all are blue. Okay, blue color represents it is passive. In the next slide, I have tiles which are red, they are active. Okay, do you see 19 slide?
Yes, sir.
Very good. I'll go back to 18. Okay, so looks like my link is better now, and because of which there is no issue on the delay. Okay, so now each tile can be either a passive tile, it is under my control. Let's say that is under my control. I can activate it with an amplification and phase tuning, or simply phase tuning. Okay, if I have that, I have 4 tiles. I can have a possibility of active, passive, passive, active, passive and passive, and passive and active and active. 4 possible combinations, right? So I can choose this combination based on 2 bits of information, right? Log 4 combinations are possible to the base 2, which is 2 bits. If I say 0, 0 bit comes, then I will say passive, passive. If 1, 0 comes, then I would say active, passive. If 0, 1 comes, I will say passive, active. 1, 1 comes, then it is passive, active, active. So this is a technique which is called index modulation. We can do it to subcarriers, we can do it to transmit antennas, we can do it to time slots, we can do it to time frequency bins, we can do it to delay Doppler bins, we can do to tiles in RIS. for conveying information bits. In other words, this HRM bits, I gave an example of 2 bits conveying through which tiles are to be active and which are to be passive. Okay, so that is what this is. Hybrid reflection modulation. In other words, the rate achieved by this modulation scheme, if I say this QAM symbols or PSK symbols are notated by this A, right, MAP-BB A, and that is the alphabet. Size of that alphabet log to the base 2 is going to be my bits per channel use. Suppose if it is 16 QAM, size of A is 16, 16 to the base 2 log is 4 bits per channel use. So this is the conventional information bits coming from this block, which is the information block. But G, I have given a notation as the number of tiles, right? 4 is an example in this case. Log 4 to the base 2 is 2 bits. So in other words, if I use 16 QAM, if I use 4 tiles and use them for phase tuning as well as the way I am describing as modulation, the number of bits you can convey is 6 bits per channel use, as opposed to passive RIS where there is no HRM bits, you will simply send only 4 bits using only 16 QAM. I believe that explains the basic possibility of hybrid reflection modulation in RIS. And this does 2 things. It takes care of the multiplicative fading to some extent, and index modulation is going to be better than complex modulation alphabets. Complex alphabet modulation means you differentiate symbols only in the 2D plane, which is real and imaginary, complex plane. But in index modulation, the dimensionality is going to be larger, so signals are more separated, so the performance can be more. So your rate can be more, your performance can be better, and you avoid possibly the multiplicative fading using hybrid reflection modulation. So this, I think, is adequate to mention about RIS in modulation mode using hybrid reflection modulation. I have given some references. We have done some work also on this, but let me skip details because of lack of time, but you can always take this as a line of new research topic into RIS if it is not talked about. Okay. Media-based modulation is also another thing which has been there from about a decade. 2013, Professor Amir Kandani in an IISc paper talked about this modulation, which is called media-based modulation. That means for channel modulation. The diagram looks very much like RIS, but only thing is this transmitter and this RF mirrors, which is also a surface, which is having, let's say, n elements we called here m subscript RF number of mirrors. These mirrors are supposed to have only 2 characteristics. If a diode, each mirror is going to be a diode. It's an RIS element, but a simple diode. If you put it in on mode by 1 bit, or it can be put in off by the same bit being 1 or 0. But depending upon the diode being in a conducting mode or in a switch off mode, the propagation characteristics in the near field of the transmitter is going to be changing. And because of that, the Hj, which is going to be at the receiver, that fade is going to be different. So a collection of these fade coefficients, which are controlled by these RF mirrors, which are in turn controlled by information bits, they create a new modulation, which is called media-based modulation. And I would say that this has been there for quite some time, but a combination of beamforming and modulation is a new line of research which is possibly good, other than performance analysis kind of papers. There are a lot of papers which are written in terms of performance analysis, deriving outage probability for various fading models, similar probability, bit error probability, expressions and bounds and approximations. In addition to that, this line of thinking for RIS will be useful for you to carry out. Yes.
Participants, please mute the mic.
Okay.
Okay,
so
sir,
I would say that we did build a real RIS based modulation, which is media based modulation. Professor KJ Vinay in our group is an RF expert, antenna expert. Along with his PhD student, my PhD student, we gave the communications theory and signal processing. They did the RF fabrication, design, and everything. We could show this diagram, what we call this as media based modulation diagram, block diagram in slide number 21, right? A transmitter here. If you see here, it's a horn antenna. The transmit waveform is coming from my instrument, but this is the RIS, which is the collection of RF mirrors, which are going to be controlled by an embedded board, which is going to convey these ones and zeros. Okay, so this was built and tested, and this is a state-of-the-art development, and it is also published in MTT, IEEE MTT transactions. So this is one line. Okay, so that brings me to the next topic, which is the sensing, radar sensing and communication, right? I just put aside, now you forget about RIS, and in RIS I talked about multiplicative fading, active RIS. In active RIS I talked about both forming as well as modulation in terms of two different modulations. Now let's go to a newer topic, which is integrated sensing and communication, which is a buzzword these days. But let me give one or two fundamental points which I want to drive at, which is important. See, first, the main thing about radar, again, if you teach radar systems course or radar engineering course these days in your courses, you will be teaching transmitter waveform, receiver waveform. The transmitter is going to be like any other communication transmitter. Receiver is also going to be more like communication, but only information bits will not be conveyed, right? You will be sending tones and so on, right? The main thing that you want to do is locate a target, right? In an environment, I give you an environment, right? Air traffic signaling, right? Aircrafts come and go, and you want to identify an incoming aircraft. In a military setting, you have jets coming at you, and you want to identify them and track them and possibly take action, right? This is the basic thing. Now, even in vehicular communication, we say that what is my environment? My environment is more like this, okay? See this scene? This is my environment. This is a freeway, and that freeway is going to have vehicles, and this is a photograph. It's a sensed image taken from a photograph camera, and in front you have these vehicles going, and this car has the radar, and it is transmitting a radar signal, and that is getting back the received signal, because I'm interested in knowing my surroundings. What is a surrounding? I should see vehicles in front of me, behind me, along the sides, and I should know how far they are and with what relative velocity they are moving. Okay, these are the two things I'm interested in. What is the location? And that is conveyed by a delay estimation in the radar system. What is delay? You transmit a signal at time t equal to 0. It goes and hits the target which you want to recognize or locate. It bounces back, so you know the echo. So you know the time it takes for the transmitter to, the transmit signal to go and then echo back, and that is delay measurement. Now I am connecting to the delay Doppler that I talked about in OTFS. Remind that is very important. In radar, what is natural is delay measurement, number one. Number two, I want to track that guy, so which means I need to know what is its velocity, whether it is going away from me, it is coming towards me, at what speed it is coming away towards me, and what speed it is going away from me. This is obtained by Doppler estimation, or more importantly, velocity estimation through Doppler estimation. So in other words, a range estimation for distance estimation is delay estimation. A velocity estimation is nothing but Doppler estimation. In other words, in radar processing, you are essentially doing delay Doppler signal processing to get the target's relative position and velocity. Okay. Now, the waveform that you're going to use is of importance to you. because now you can see in this picture below, radar sensed scene is right below. Okay, right below. Can you make out anything out of this picture? See this on the x-axis is relative velocity. I don't know, maybe I should maximize. People have put up with me for long. I did not maximize this, realize that.
Sir, I think while
Okay.
maximizing, we have a problem in the PDF.
Oh, I should go back?
Yes, sir.
Okay, so can you see?
Yes, sir. Now it's fine.
Now the bottom diagram, it says relative velocity in meters per second. On the x-axis is range, which is distance in meters.
Bye-bye.
So
Bye-bye.
this,
Bye-bye.
okay, I think it
Sorry,
is.
sir. You can please
No,
continue.
it's okay. I'm fine because it is a Saturday. People have family time and everybody has to be with their family. But we are here talking about 6G and technologies. But that's how it is. Fine.
Okay.
So it's fine. So relative velocity
It's our
is.
pleasure, sir. It's our pleasure, sir.
No. Yeah, I understand. I fully understand. I know. There is no issue, and it is. At the end of it, everybody takes if one or two good messages from the talks that we have had, maybe in this thing. That is good. I think that is the main aim. So intermittence can be okay, fine. We always have something or the other. Okay, so here velocity, that is Doppler, range, that is delay. Now you can map. Essentially, a blue is a very strong echo. See the bar, which is the amplitude bar, or power, received power actually. The color map or heat map, we call this, right? Heat map of the received signal. Blue is very strong, 10 dB, right? Let's say. And you can see the guy who is most strong is at the 0 point. What is 0 point? 0 delay, 0 Doppler. Now 0 delay and 0 Doppler is at the location of the transmitter itself. So what that means is this truck in which our vehicle or the car in which this transmitter is mounted, and that is being measuring the radar signals, being a self reflection by itself, because the object itself is a big object. The car itself is a big object, and it is reflecting its own signal, which is very nanoseconds kind of a thing, which is very close to 0 delay, and that is the strongest signal. Okay, but interesting thing, you have targets 2, 3, 4, 5, and 6. They are all corresponding to the cars in front, and you can see they are in the lanes also to the left, right? Can you identify the lane in this picture? That is the range. It's to the left. There is 5 is somewhere here in the other lane. In the same lane is 3 here. 4 is in the farthest more, which is here, 6. So in other words, range gives you the location, and Doppler, when I say Doppler, 0 Doppler, see to the left is negative Doppler. Negative Doppler means what? It is going away, right? It is going away. So that also tells you that the cars in front of you are going away from you. Their speeds are more. You can see their Doppler, they are maybe slower or faster. They can all be decoded. So to give this picture is important to me, because whatever you do in terms of research later is to essentially get this picture for the autonomous driving engine, meaning engine means the hardware and software that drives it, to exploit it. You may ask why this map is required, because it is so blur and all this. And to me, it is very important for me, because if there is rain, if there is fog, if there is night, if there is bad weather, your other sensing will not work, but microwave sensing will help. And that is one of the important things about all weather sensing is going to be useful. And that is one of the important things for vehicular radar in our new information about intelligent transportation systems. Okay, so now the question is, what is the waveform that is used? That waveform which is used is in here, which is given in this paper way back in 10 years back. If I look at it correctly, it is 2010 or 11. Okay, so it is a OFDM waveform. Okay, so in other words, combining a waveform for both transmitting information to this car For example, this OFDM transmitter, if it transmits this binary data to the, this is the base station and this car is the customer or the user, this information goes, that is the regular communication channel. But the same signal, when it is reflected as an object or a target by the car, to be sent or reflected, echoed back to the signal, to the base station, right, is going to be allowing it to figure out what is the range and velocity information about this car, which can be used for very many purposes. Okay, so this picture is using IFFT and FFT. It is a OFDM waveform. I claim one more point. OFDM signal is not good for communication when it is doubly selective channel. I'm going to say one more point. OFDM is not a good waveform for good radar tracking, although this shows good performance. The performance can be much better if you use better waveforms, which are localized more and more in the delayed Doppler domain. Let me emphasize the point. A target can be, if two targets are near, if the echoes are going to be blurred between these two, you will not be identifying these two targets as two separate targets. So in other words, the auto ambiguity of the waveform, when I say auto ambiguity, a waveform correlated with itself is the auto ambiguity function computation, right? If it is very narrow, then what that means is that if there are two targets, those two targets will create two different peaks, identifying themselves as two different targets. You can see that there's a blur around these red markers in this diagram, and that is the effect of the auto ambiguity of the waveform which is used, which is OFDM. The message is OTFS is a delayed Doppler waveform, and it is localized in the delayed Doppler domain much better than any other waveform. That is a message. Okay, so I did not spend time about this diagram, which is, again, please go and see. A wireless channel should be wireless channel should be represented in the delayed Doppler domain, and that is this message, right? When you represent this channel in the delayed Doppler domain, only three tuples are of interest. One is the delay due to the target or the cluster. In fact, what we say is you have a reflector. I have dominant reflectors, buildings, bridges, big objects. They are the dominant reflectors. These reflectors are at a certain distance and they are at a certain relative velocity. So they point a delayed Doppler point in the grid, which is the delayed Doppler grid. And the height tells about the reflection strength. Okay, so in other words, the channel response, we should be talking about h tau nu, not ht. Linear time invariant systems, in your signals and systems, you will be saying impulse response h of t. You give a delta of t at the input and c at the output, and that is h of t. That is the impulse response of the system, right? Now that is the old time thing which will continue to be true, but the newer thing is I can view the same channel, the black box, which you call, I characterize that box as h of t. I can represent that box as h of tau comma nu, which is two-dimensional, right? And one is delay, one is Doppler, and tau nu corresponding to each reflectors is going to be my prime importance. Those are the vertical pillars like kind of diagrams that I've shown, and they are the targets. If they are weak, that means they are small in size or not dominant. If the height is more, the echo is more, and so on. So this view is important to carry, right? So this is one message I can say. Why OFDM or any other waveform is not as good compared to the so-called delayed Doppler pulse that I talked about for modulation. Now I'm talking about delayed Doppler pulse as for radar sensing also. Why both have to be combined? Because cost can be reduced. I think I did not highlight one here. See IISc advantages, the bottom bullet, third big bullet, better resource and bandwidth sharing. Because suppose if I have a radar signal on hardware and it is using some other bandwidth, some other frequency band, it is going to be extra resource for both. Communication resources are different, radar sensing resources are different, their hardware is different, these people are, this hardware is different, and they will EMI wise, they will interfere with each other. Electromagnetic interference point of view, they can interfere with each other. All these things can be avoided if I can combine one waveform to do both, right? So better resource bandwidth and resource sharing, reduced system complexity and cost, and reduced EMI related issues. Why IISc is important and why waveform is important is better the delay Doppler localization of the pulse or waveform that you're going to use, better will be the radar performance. Okay. Time domain modulation. If you use a single time pulse, narrower and narrower time pulse, if I use, that is good for delay estimation to be finer and finer. In other words, the range prediction can be very good. If I want to have a target, I want to establish its range only, then a narrow pulse is good. And likewise, I want to say, I want to estimate only the Doppler or the velocity of a target. In a narrow frequency pulse is the best. Okay. But both are not going to do the other function. In other words, a time domain pulse will do well for delay estimation, but poorly for Doppler estimation, because a very compressed time domain pulse is a elongated waveform in frequency. In this figure, that green ellipse, right? As you compress time, frequency will expand. So it is not localized in the frequency domain. I use a very narrow frequency pulse, which is this red ellipse. It will be doing good for velocity estimation, but it will be stretching along the time axis. So in other words, Heisenberg uncertainty principle says you cannot do compress in time and frequency simultaneously. Okay, that is one of the problem. And people use linear frequency modulation, chirp waveforms and other things to overcome this problem. If you use a pure time domain pulse, it is good for delay, not for Doppler, because it is not localized in the frequency domain. If I use a very narrow frequency domain pulse, it is good for range prediction, but not good for delay because of the dispersion. Now, you have to have a waveform which is localized both in delay as well as Doppler, not time and frequency, by the way. Ultimately, we are interested. Delay is time, of course. Doppler is frequency, of course, but then they have different transform relation as dimensions, right? So now if you do delay Doppler waveform to be localized with this exact transform waveform, the pulse zone that I talked about in the previous slides, like whatever I showed as a pulse train modulated by sinusoid, that if you see the so-called auto ambiguity function, that look like the right hand side picture, and that has the box which is the narrow blue dots, and I have to process only the small rectangle around that. So which means all other guys will be not going to interfere, and I can only take the blue which is in the blue box, and that is going to be giving you much better resolution and ambiguity resolution in radar performance. So to say again the summary, what we say is it is going to be OTFS delay Doppler waveform, which is pulse zone, or a delay Doppler pulse, is going to be much better than any other waveform for Doppler delay Doppler estimation, which is radar sensing objective. So in other words, ZAC OTFS is going to be a natural blend for communication, as I told in the first part, and the third part I am saying it is also good for radar. For IISc, new research can take on combining these two in the OTFS framework. You can do other waveforms also. So I have 2 more minutes. I'll spend maybe 3 minutes more, which is 5 minutes, to introduce near field communication. Okay, terahertz I will skip because it's RF and a lot more things have to be done, and I don't specialize on that. But near field communication, you may think it is RFID like near field communication, right? It is not. The emerging NFC in our community, which is emerging as a new topic, the name is the same. RFID communication also is near field communication. But what we talk about is also near field communication, but different. Okay, so that's what I'm saying. Not RFID like distance sense, few centimeters. No, we are not talking about that in NFC. We are talking in terms of EM theoretic sense, electromagnetic theoretic sense. Okay, and that is to say if I use very high frequencies like millimetric wave or terahertz frequencies, number one, or now I have antenna arrays which are 128 antenna elements or 256 antenna elements and so on in the massive MIMO systems. If I go extra large MIMO, right, thousands of antennas, which I call that as very large.
Participant, please mute your mic.
Okay, so large antenna arrays, if these two happen in 6G and beyond, it is going to happen most likely because we are talking about extremely large MIMO on the one side, millimetric wave or terahertz on the other. Use of these two put EM theoretic understanding or behavior at focus. That is a message, and that creates the notion of a near field communication, which is in one slide I can show here. See this. There is a transmitter on the left. There is this bullet point, right? It is transmitting. There are different distances that I show on the x-axis, right? And I show one which is far field, and to the left of this I have near field, and near field I split it into two. I say reactive near field and radiative near field. Okay, what is the difference? In the far field, the radiating EM wave will look planar. It's a planar wavefront, right? Whereas it doesn't become planar wavefront from distance d equal to 0 onwards. It will start as a spherical wavefront and slowly it will graduate itself into a planar wavefront. Now, which means at some boundary, which we call this as Rayleigh distance or Fraunhofer distance, to the left of this are distances to the left of this Fraunhofer distance, which is going to be given by 2d square by lambda, where d is the antenna aperture. Larger the antenna array size, 1024 antennas versus 64 antennas. 64 array aperture is smaller, but whereas 1024 is much bigger. So d is the antenna aperture. So larger the aperture, the Fraunhofer distance is going to be affected by quadratic term, that is d square. And smaller the lambda, again millimetric wave and terahertz, if they are very high, lambda is going to be very small. In other words, the effects of larger distances and smaller wavelengths in this case is going to decide my Fraunhofer distance. And so far we have been operating up to 5G, right, where my D, choice of the aperture in terms of antenna size, aperture size, number of elements, antenna elements, and the carrier frequency, which is 6 gigahertz, 5 gigahertz, and so on. Those distances are putting these users in the far field. In other words, the Fraunhofer distance is going to be in the order of a meter or so, or in sometimes centimeters. Okay, so typically a base station is 7, 10, 20 meters from you, so which means you are in the planar front regime. So channel models, algorithms and techniques, beamforming, beam steering vectors, they're all under the assumption of planar wavefront. But what happens to this Fraunhofer distance when d is very large and lambda is very small? In the next slide, I can show that if I have 60 gigahertz millimetric wave and 0.5 meter, half a meter kind of aperture having large number of arrays, the near field distance, which is the Fraunhofer distance, is going to be 100 meters. And that is large. Okay, you are going to see at this very high frequencies and large aperture sizes, you are going to be in the spherical wavefront regime. Your user, if you are a user from the transmitter, which is the base station, you are going to see a spherical wavefront. The channel model and everything are going to be different. So in other words, whatever we have assumed so far worked very well for the planar wavefront. For these two reasons of antenna aperture size in terms of array sizes growing extremely high. See this emerging trends in 6G and beyond is tremendously high frequencies, terahertz example, extremely large scale antenna arrays, thousands of antennas, new types of antennas using metamaterials. Somebody must have talked about some antennas. I saw some speaker in the first day on antennas. Metamaterials are going to be used. Those combination of 1 plus 2 plus 3, tremendous high frequencies, extremely large scale, new types of antennas give a new paradigm shift to EM characteristics. In other words, you will be in the near field. It could be 100 meters. It's not 2 centimeters like RFID.
Okay.
It could be 100 meters, but you will be in the spherical wavefront. So what? Okay. So what? There's the last slide. Okay. So what? The interesting point is, suppose if I have an array, n is the array size, n elements are there with distance being d, and that lambda is another factor, and this is an object here. I want to steer my beam towards that. I have a beam steering vector, right? And that beam steering vector for each of these elements, n equal to 0 to n, that is going to be given by this if you are in the far field, if you are in the planar wavefront. But if you do math and the EM modeling and the equations based on the EM theory, then if you are in the spherical wavefront, the same beam front, the steering vector is going to have an expression like this, which is in addition to these terms, it is going to have D, which is the separation to be inside, and N, which is going to be the element of the index of the element. They are all going to come into the play. So in other words, your beam steering vectors are going to be different. If you are in the near field and if you are beam forming, you are using a far field assumption, you are going to have an inaccurate localization. But if I can say, if you are in the near field regime, if you use the near field steering vector as given by this, you will be having better localization, better communication. So a lot of now new modeling, channel estimation, signal processing, performance analysis are geared towards this NFC, not RFID like NFC, but this Fraunhofer distance based near field possibility when extremely large number of users, antenna array elements are used. It is transmitter side, not RIS, right? It is in the transmitter. And high frequencies and metamaterials for the antenna types. So they lead to this. So new line of research one can look at. So that brings 6 minutes past, or 7 minutes past 30. This is the summary slide I want you to go through. We say wireless systems are continuously evolving. What is objective? To offer better service with increased capabilities. Each generation should give me more capabilities for the customer, user, and for the operator. It should give them profits, and both should be satisfied. Only then a generation is going to be a successful generation of a network. And 6G presents an opportunity to reflect on wireless communication fundamentals and innovate. The linear time invariant versus linear time variant framework, and this in the NFC definitions in spherical wavefront versus planar wavefront, and RIS being used in the active mode for modulation purposes. They are all new innovation possibilities, asking basic questions about our past understanding and how to innovate into new understanding. These are several topics which I talked about. And I would say beyond this, what quantum communication, I always wonder what may happen. And that may be far off into the time, but it makes me to feel good to think about what will happen if quantum communication comes, because it is an opportunity. But I don't know, I myself don't spend time on research on that because I don't understand much about it. But that's how every research starts. You don't understand much about it, but then you are curious, you go out and fiddle around a little bit, and then talk to people who know more than that, more than you, and then understand, and then try to evolve yourself as a continuous learner. So with that, I'll stop. Thank you very much. So I have taken close to 10 minutes more than 6:30. Thank you.
Thank you, sir. Thank you so much for the wonderful technical session. I would like to take the questions from the chat box and repeat to you, sir.
Yeah.
How can reconfigurable intelligence surface be effectively integrated with existing 5G infrastructure to pave the path for 6G networks?
Okay, so this is a question which I will be least qualified to answer. Okay, although I worked in industry in the past, I interact with the industry a lot. As a technology, it is a technology which is a useful technology, but it has to mature quite a bit to a level of commercial deployment. When you say existing 5G, how it can be integrated, I think the question is related to commercial deployment. But there were several RIS lab demonstrations have been there, right? If you see the literature, a lot of universities, labs, they have demonstrated RIS. Even in our own IISc, people have built. But then to a commercial deployment, I may not be the right person, but it is a useful technology for consideration into improving the quality as we hypothesize.
Okay, sir. Moving to the next question. When RIS is used for vehicular radar communication, how much power it consuming?
Okay. See, as RIS may consume very little power because the very nature of that is going to be very small power required to tune that the electronic circuits, which could be simple embedded systems, right? Whatever that small embedded boards that you have, such an electronics is good enough to do the so-called tuning part. But the channel estimation part, which I think is a research topic, that may consume more resources in terms of power. So as long as you don't use active elements in the RIS, the power consumption may not be very high. Not like a base station power with 100 watts antenna to a 200 watts kind of power amplifier or 100 watts power amplifier, 50 watts. It may not be. It is affordable. That is one of the good things about it and why it is attractive. See, alternatively, let me put it this way. This is again an academic perspective or a systems engineer's perspective rather than an operator's perspective and a business person perspective. If I have to engineer a beam towards the receiver with the existing technology, I have to have multiple elements at the transmitter itself. When I say multiple elements at the transmitter itself, I am talking about multiple RF elements, multiple RF chains, which means by the design, it could be having more components in terms of hardware, right? Up converter and so on, everything. It could be a mix of digital and analog, but it could be expensive in terms of hardware. But RIS can be simply a reflector, which could be a small passive devices. Very little power is required to operate them. So I would say that compared to transmitter being asked to beamform for you, asking RIS to beamform for you may be cheaper in terms of power consumption. Complexity may be another issue, and then where to deploy and other things are all engineering questions. But power consumption wise, there is an attractive feature.
Okay, sir. Moving to the next question. What modulation works best with RIS with multiple users?
Okay, so it depends upon again what is the channel that you are going to deal with. If you're going to deal with the existing channels, then existing waveforms will do. If you expect my frequency allocations are going to be different for 6G, so from 6 gigahertz it is going to be given as 10 gigahertz or 8 gigahertz 7. So there may be relative phase Doppler shifts, and because of that, if the channel response is going to be different, then we may have to look for different modulation. As of now, OFDM has been proven to be good. That's what I would say. But nonetheless, it doesn't stop us to look for better waveforms than that.
Okay, sir. I'm moving to the last question. Distance coverage by RIS.
Mm-hmm.
How much is the distance coverage by an RIS? That's the question.
Okay, so this is again an engineering question. So that is again going to be the reason why active RIS is needed. Okay, I think this comes, I'm not giving a hard number like 10 and 15 because it is not built commercially and tested in a real field in a big way. Okay, I'll put it this way. There is a multiplicative fading that I talked about. So that restricts the coverage. Okay, if you have to have more distance, you have to have more power, which is going to use more transmit power from the transmitter, so that the reflected power also will be more. But there is a beam forming effect which is going to help. But to increase that limitation, RIS is being talked about now. You can make some elements to have amplification. If that amplification happens, then the coverage can be reasonable in practical terms.
Thank you, sir. There are no more queries from the chat box. I would like to call Sudarshan, sir.
Yeah.
Yes, sir. You have. I am handing over the session to you.
Thank you, Sainath. Sir, first, big thanks from us to you for accepting our invitation and delivering such a wonderful talk. We hope to host you at NIT Trichy sometime soon, physically. Thank you, sir.
Okay, so to give this talk, and I did not expect the participants to be so large in number. I don't know what trick you did to attract so much of participants, but thanks for all the participants at the late hour on a Saturday.
Sir, you being one of our
Thanks to
speakers
you
itself is a big
inviting.
advertisement for us.
Okay,
Sir,
so
I just have one
that is
question
nice
on
of you
this.
to say.
Yeah, I have one question. Can I ask?
Yeah, please.
Yeah. So just like we have this SWIFT, simultaneous wireless information power transfer. In this integrated sensing and communication also, is there? Can power transfer also be an additional research
Integrated.
topic to look? Yeah.
Yes. I did not talk about other topics because that will be too thin. As such, I felt that I'm just highlighting only the big bullet points, and also Swift is an area that I'm not doing work on. So many a times I prefer to talk on what I closely work on to a large extent. But nonetheless, you can say that wireless power transfer is a big interesting topic, and there are a lot of again relaying, because all the research that happens in cooperative communication in terms of cooperative relaying, they all have shifted to RIS. So all the questions that we asked about in cooperative relaying, including the simultaneous power transfer and other things, they can be posed in the RIS setting also.
Okay, sir. Sir, another request is we would like to have at least one of your lectures in NPTEL so that all of us can use it on some advanced topics of 5G or something. So it'll be much more beneficial. That's a request from us.
Oh, thank you. I'll keep that in mind. I never did one NPTEL. I don't know why, but there were requests in the past, but somehow I make it a point to go and then give talks whenever an opportunity comes. In fact, I came to NIT Trichy when your students conducted a tech fest or something. What is that name? They had a tech fest game.
Probe.
Yeah, something. They invite people and they invited me. I came and I met your topper at that time, Yashwant, in that batch, and he is our current PhD student in IISc. So I visit places to the extent that I can travel, and online makes it even more convenient, but I always prefer to visit to have a more direct engagement rather than online. So anyway, that's a old-time thought, but the newer thing is online is here to stay, so I have to deal with that. So that is also fine, but definitely NPTEL, I'll think about it. Yes.
Thank you, sir. Thank you. Thanks for your time. Thanks for joining. Thank you, sir.
So thank you so much, and appreciate your invitation, and then let me log out, and then thank you.
Thank you, sir.